All right, guys, so I believe this is lesson 4.3, which is talking about simple harmonic motion. So we're going to start with mass spring oscillators, and then in the next video for next week, we'll get into pendulums, which is pretty similar, just, same ideas of concepts of simple harmonic motion, just a different device. So simple harmonic motion is just a repetitive motion that occurs when there's a restorative force acting on an object and it's proportional to its displacement. So what that means is there's this force that is trying to restore the object to its original position, and that force, the size of that force, is based upon the displacement from its original position. So examples of simple harmonic motion, pendulums, spring oscillators, mass spring oscillators, those are the two that we're going to follow and look at. And spring oscillators is the focus for today. The equation that we're talking about that it follows, or pendulums don't follow exactly this, but it's close enough that we use it. It's this equation here. So this equation is known as Hooke's law. So Hooke was an English scientist who studied springs. So it's called Hooke's law, named after him. And the equation is Fr for restorative force equals negative Kx. So negative is just the direction, and K is the spring constant, which you're familiar with from the energy equation that we had with elastic objects like springs. And then X is how far it's stretched. So these two letters you should already have a concept of. Fr is just like the force that is proportional to it. So if you imagine kind of a spring, so let me draw a spring down here, and we'll put a mass on that spring. And let's just say it's not stretched at all. So it's here at this kind of dotted line, and that's where X is equal to 0. So it's not stretched, it's not compressed, it's just kind of relaxed. So there is no force, because if you had X equal to 0, then the force would be equal to 0. And if you imagine, okay, I'm going to take this mass and move it over here. So I'm going to apply a force and pull on it. And because I pull on it, the spring will get stretched out all the way to kind of this position, right? So there's this displacement, and however far you stretch it or compress it, I could pull it the other way, that's X. So I have a positive displacement here, and what does the spring want to do? It wants to pull, and it wants to pull back onto where it was going. So it wants to pull it back towards the relaxed position. So this blue arrow that I drew in would be the restoring force, and that restoring force is in the opposite direction as the positive X in this case. If we did the opposite thing, so if we had the same spring kind of set up, so originally it's at the equilibrium position again, so the dotted line is X equal to 0, say, and this time instead of compressing it, we're going to apply a force, so Fa for the applied force. We pulled it this one. This time we're going to swish it in, so we're going to push in on this, so I have a negative Fa, and because of that, the spring would get compressed, right? So there'd be lots of coils in this section, and however far I compressed it, that would be measured as negative X. So like whatever distance that was, that's how far I've pushed it in. And because of that, the spring is going to try to push in the opposite direction of that. So the restoring force in this case would be positive. So basically what you look at is this displacement is either positive or negative, and the restoring force always goes the opposite way to that. And if X is equal to 0, there is no restoring force because it's not stretched or compressed. All right. So some factors that affect the restoring force when you're applying it to a spring mass oscillator. The spring constant K, so that has an impact. So the force is stronger the bigger the K value. That makes sense, right? Because the equation is F equals negative Kx. So it's a direct relationship with X, or with K. It's also a direct relation with X. So if either one of those factors gets bigger, the restoring force, Fr, would get bigger. Displacement or compression, that's the X factor there. All right. So you can make a graph of force versus displacement, and you would get this constant slope, which is the spring constant. One thing you should notice, though, if we come back to this idea with the picture where I drew the spring and the mass. So as I pull or compress this more and more, that force changes. So this is a non-constant force. So if the force is not constant, as you can see, like as this value gets bigger, this force gets bigger. So as this force changes, that means that we can't use typical kinematics equations to calculate them, because all those equations that we had in kinematics to establish position and velocity and acceleration and time, those are based on a constant acceleration. And if your force is non-constant, then your acceleration is not constant. So you can't use those typical kinematics ideas that we do. This here is just our spring potential energy equation. That's going to come into play here, and we're going to use that a lot. So again, 1/2 kx² is what we use for that. So some terminology that we've learned over the course of studying rotation. So a cycle or an oscillation is just one complete movement. So if you look at this GIF, I'm going to start here where it like stretched out all the way, and it goes over to where it's compressed all the way, and it comes back. That would be one cycle or one oscillation. So that from going from one point back to the same point in the same portion of the cycle, that's it. Amplitude is just the maximum displacement. So if we look at this as our total displacement from our maximum amplitude to our positive A to negative A, the equilibrium position should be halfway between those. So it would be somewhere in here where it would be relaxed, and this is like the zero position. That's the equilibrium position. So you had a positive amplitude going this way and a negative amplitude going to the left, positive and negative for right and left. So A is amplitude, T is the period. So if we timed how long it would take from going from this point all the way to that point and back, that would be the period. And the frequency is just the inverse of the period. We studied that earlier in the unit, so that should still make sense. So another term that we're going to study is called angular frequency or angular speed, and that uses the same equation, or not same equation, but the same letter to represent angular speed that we did before with like rotational kinematics. So omega represents angular speed, and the way that works, it's just 2 pi times f. So it's saying basically the number of times it would complete one cycle or one circle. That would be 2 pi times the frequency. So if you know the frequency, you multiply it by 2 pi, that's going to get you the speed. Okay. Well, with the factors that affect the period of a mass, I don't have the demo set up here at home, but we'll be doing that in class, so we'll come back to that. But we're going to talk about it. So if you're probably watching this after we did it in class already, but the factors are based on this equation. So this equation is the equation that we use to solve for the period of a mass on a spring, or a spring mass oscillator, mass spring oscillator. So it's 2 pi square root of m over k. M is the mass that's actually on the spring. K is the spring constant of that spring. So as the mass increases, the period also increases, and that makes sense, right? Because like it's going to go, if you imagine this mass on a spring, so again, I'll draw the picture, and we're kind of pulling it and then going to let go, and it's going to oscillate, so it's going to go over and back, and that would be one period. The more massive this mass is, the more resistance to change in motion it has. So it's got more inertia, which means it's going to kind of take more time. So that makes sense that it would go slower. K determines how much force is there, because F equals negative kx, so that restoring force. So as you increase the strength of the string, you make this K value larger. The restoring force is also going to get larger. So if you have a bigger force acting on the same mass, you're going to have a quicker or a bigger acceleration. A bigger acceleration is going to mean it's going to move faster, and it's going to take less time to do that. So that one is inversely related. So as K increases, as the force gets bigger, the period gets smaller. So that's kind of that. Notice that x is not a factor in this equation. So x does not have any impact on the period. So I can stretch it a little bit, or compress it a little bit, or I could stretch it a whole lot, or compress it a whole lot. And the amount of time that it takes to complete the oscillation is the same. So it's 2 pi square root of m over k. That's the period equation for a spring. Frequency, again, is just 1 over f. So you could take our f is equal to 1 over t. So if you do and flip this over, it'd be 1 over 2 pi, and you take the square root and you flip that, and it'd be k over m. So you could do it that way too. I usually solve for a period and then just do the inverse to get the frequency. So I use this relationship here and solve for f, which is that equation. There is also this idea of angular frequency. So 2 pi f, that's just omega. We established that on an earlier slide, and that's just equal to the square root of k over m. So like if I multiply both these sides by 2 pi, so it would be 2 pi f equals square root of k over m, and that's omega. So just another way you can kind of work through these ideas. Omega is going to come up later in other situations, so we'll do that. So in this first one, it says a block of mass 2 kilograms is attached to a spring whose constant is 300 newtons per meter. We want to calculate the frequency and the period. So we're trying to figure out F, the frequency of this oscillation, and the period. Again, I always usually solve for period first, so I use T equals 2 pi square root of M over K. So you would just plug in the values from the problem. So M is 2, K is 300. You're going to take a square root of that and then multiply it by 2 pi. If you do that, you should get like 0.513. So it's a little over half a second for the period. And then the frequency, you just do the inverse of the period, or 1 over t. So, well, that's supposed to just be a t, not a tau. So F equals 1 divided by the period. So it would be 1 divided by 0.513. And if you do that, you get something a little less than 2. So it's 1.95 hertz. So it does almost 2 oscillations per second, but it's a little bit less than that. Okay. So so we've looked at kind of the period equation. We're going to come back to this idea of energy and thinking about energy. So I have this block oscillating between point A, point B, point C, and it's going back and forth and back and forth. This is a really good visual about the restoring force. So again, as you can see, the position goes to the right, the restoring force is in red going back to the left, or as the position goes to the left, which is negative, the restoring force is back to the right. So I think that's a good visual of what's happening with the force. And you can imagine the energies and the ideas as we go through this. So let's kind of look at these different factors for position, which would be like the location, or x, the velocity, how fast it's moving, the force, which is like the restoring force, like what's the force acting on it, the acceleration it's experiencing, and then the potential energy of the spring and the kinetic energy of the mass spring oscillator. So we're looking at kind of the energy of the mass and the spring together. So for the position, I can't pause this, but if you imagine it's at position A here, that's at the maximum negative. So I'm just going to say negative max. All right. At B, x is equal to 0. So it's not displaced or compressed at any point. And then at C, it's at the positive maximum position. So I'm just kind of filling these out and looking at what's going on as time goes by. All right. For velocity, if you look at the 2 extreme points, that's where it actually stops momentarily. So at A, it stopped, and at C, it stopped. So that's going to be 0, and that's going to be 0. And at B, it's moving. At B, it's actually moving the fastest. So this is going to be the maximum here. And it could be moving right or left. So I'm going to put a plus or minus in front of it. So it's plus or minus the maximum velocity. That's what's going on in that one. For the restoring force, we've kind of talked about that. So at A, and then you can just look at this area, the restoring force at C is a maximum and it's going negative. At A, if we look when it gets to A here, it's a maximum and it's going back to the right. So that would be a positive max. And when it's at position 0, there is no restoring force, so that's the force is equal to 0. So that's just using that equation again. For the acceleration, thinking about the acceleration, if you just use Newton's second law, so the net force is the restoring force. So like these are the restoring force, and that's equal to ma. All right. So is mass changing? No, it's not. It's a constant, so we don't really worry about it. So A just does whatever F net does. So this would be a positive maximum acceleration at the negative position. So that's where it like is accelerating back to the right, the biggest. So when it gets back to here at A, that's where the acceleration is the largest going to the right, because that's where the biggest force going to the right is. Same idea, just opposite kind of direction with C. So when it gets back to C over here, where I get my mass over here, the biggest restoring force is going to the left, which means the biggest acceleration is going to the left. At B, there is no restoring force, so there is no net force, so there is no acceleration. And then we're just using the energy ideas. So for 1/2 kx squared, half isn't changing, k isn't changing, x is changing. So it's based on x, so whatever happens to x, that happens to us. So when it's at position A, that's when it's at a negative position, maximum position, but it's a negative squared, so it's a positive. So it's just the maximum value here. You can't have negative potential energy in a spring, so that's positive max. At C, it's also at its maximum displacement. It's just stretched this time, so that'd be a positive max. There is no potential energy when it is not stretched, so when it's at B, it's at 0. And then the reverse happens for the kinetic energy. So at A and C, it's stopped. So if you look at the velocity, if the velocity is 0, the kinetic energy is 0. So those are both zeros here. And then the maximum kinetic energy occurs when it's at a max, and you can't have negative kinetic energy. So that's a positive maximum. Okay. So we're going to kind of, now that we've analyzed this mass spring oscillator for various ideas like position, velocity, force, acceleration, spring potential energy, and kinetic energy, we're going to graph them. So we're going to kind of look at these points, and we're going to graph based on those points. So I have a table here, and we're going to say, okay, this line here is 0, and this would be like the maximum positive, and this would be the maximum negative. So that's our kind of default. And we're going to go from position C to position B to position A, back to B, back to C, back to, moving back and forth. So if we start here, we're at C, so I'm starting now. We're going from C to B to A, back to B, back to C, and then the process starts over again. So looking at we're just kind of fill in these. So we're starting at C, we're at a positive maximum. So if I was plotting a point, and I'll use a pen that looks sort of different. Okay, so at C, we're at a positive value. At B, we're at the equilibrium, so we have no displacement. At A, we're at a negative, and then B, we're back at 0, C positive, B, and we keep repeating ourselves through that. So if we connect that with a graph, and you look through this, this looks like one of our trig functions graphs. And this is a cosine curve, because when you are at the maximum at the beginning of the cycle, or we're at position C, that's where we're at our maximum position. Okay, we can do the same thing for velocity. So thinking about the velocity, it's moving fastest. We're going from C, so at C it's at 0. So again, I'm going to plot the kind of positions here. So at position C, it's stopped. At position A, it's stopped. So I can fill in all the C's and A's for that. And then if it's going from C to B, that's actually moving to the left. So that's a negative. From A to B, that's moving back to the right. That's positive. So it's doing this kind of cycling. So it's a different kind of graph here. So kind of looks like that in our curve. And again, from positive, 0, and negative for those. So we're just kind of graphing these out. Again, positive, 0, negative. When I'm at C, I have the biggest negative, position for acceleration. So I'll use a thing here. So I'm down here. At B, I have no acceleration. At A, I'm maximum going to the right. So it's going to kind of cycle through and do this repetitive pattern going that way. And I could graph that out. So it's a little bit thinner compared to the last one. So it's going kind of like this kind of graph. And again, these are all sine or cosine curves of some sort. The force is exactly the same. So positive, 0, negative. Force is exactly the same as acceleration, because the only thing that's different is mass. So it's going to look like this. Come back. And then the potential energy and kinetic energy, those are a little bit different. And again, I'm just kind of taking you through these pretty quick. But again, we're going C, starting at position C, and then position B, and then position A for all these. So CBA, and then starts repeating back the other way. So A, B, C. So we're starting at the kind of maximum position. It's stretched out. And then it goes to B, which is equilibrium, and then A is when it's compressed the most. So we're going like this in all of these and through. So that would be one cycle. So looking at this graph, so at C, it's got a maximum energy. At B, it's at 0. A, it maximizes again. It's not going to be negative and positive, though. It's just going to kind of repeating. So it does something like that. And then for C, that's where it has 0 kinetic energy. And then B is a maximum because it's moving fastest. And then it comes back down. It's going to oscillate back and forth like this for all these. And if you look at these kind of graphs, they are the opposites of one another. So this is like 0 and this is the max. That's positive. This one is 0, and this is the max again. So like when the spring potential energy is at a maximum, when it's stretched or compressed at the maximum point over here at C, or over here at B, or A, sorry, the spring potential energy is the biggest, but the kinetic energy is the littlest. And then if we're in the middle here, the kinetic energy is the most, but the spring potential energy is nothing. If we added these two graphs together, so if I come back down here and I add the spring potential energy and the kinetic energy, that gets me the total energy, and we would just get a straight line. So the total energy would just be a horizontal line going across like this, because when you add any of these points together, you always get this maximum amount of energy. So again, conservation energy makes sense. It's just at different points in this oscillation, the energy is formed by adding potential and kinetic together. And that was like a question on your last test where you had to do the same kind of work. So we're going to do that again, just with a energy relationship with this mass spring system. Okay, so we're going to work through this problem. There are lots of parts in this problem, so I'm going to try to go slow and make sure that it makes sense. There isn't too much really after this problem, so I know we're getting a little longer in the video, or actually I'll probably I'll keep going, but let's go through this. So it says ideal harmonic oscillator, so that's just the mass on the spring, has a mass of 2 kilograms, a force of 20 newtons stretches it to a displacement of 0.5. So so we know M, we know X. It says to find the spring constant, so the spring constant's K. So we know the force, so we should use the restoring force idea. So the restoring force is equal to negative Kx. So when I do this, I could say 20 or positive 20 or negative 20, it doesn't matter. So the restoring force would actually be going the opposite way, so it'd be going back to negative direction, and it'd be negative Kx, and X is 0.5. So if I multiply both sides by 2, that'll get rid of the 0.5 on this right side. So K, the value for K, is 40 newtons per meter. So you can't have a negative K value either. You always have to have a positive one. So 40 newtons per meter, that's that. For the total energy, if it's stretched to the maximum distance, so the maximum stretch is when it has all energy in the form of potential. So that'd be 1/2 K. And then if we wanted to use X squared, that's fine. It would be the maximum distance. We could also, the maximum distance stretched is also known as the amplitude. So if they use that terminology, that's fine. So it would be 1/2 40. And then this would be 0.5 squared. So if you do all that and you put that in your calculator, you get 5 joules of energy. So there are 5 joules of energy in the system. It says, what's the magnitude of velocity at the equilibrium position? So this, again, we're thinking about this oscillation. So if, let's say this is the equilibrium position, and it's oscillating from the maximum position going to that, then compressing to whatever that maximum compression is, and then it comes back to the equilibrium, and then it moves through the equilibrium and goes back to its original position. So like this is just kind of watching that oscillation occur that we've had in our simulation or in that GIF for that whole time. So it's oscillating through these positions. What's happened here is this was the maximum spring potential energy, and all that spring potential energy is now changed into kinetic. So we can say the spring potential energy at the maximum is equal to, when it's at the equilibrium position, it's all kinetic energy. So it's the maximum kinetic energy. So we basically just have to say 5 for the energy for part B that we found is equal to 1/2 K, or 1/2 mv squared. So m was the mass of the block, which is 2, and then it's v squared. Half of 2 is just 1, so that's easy, and then we just have to take a square root of both sides. So V is equal to something like 2.23 meters per second. So again, it's just using conservation of energy. We're going to do this a couple times. I'm going to skip over some of these because they get pretty repetitive. So I'm going to skip E because it's basically the same as D. So at D, it says, what's the magnitude of velocity when X is equal to 0.3? So, so this position out here is 0.5. This position here is 0. And 0.3 is somewhere in between. So let's just say this is 0.3. So if this is the displacement of 0.3, if we think about the energies that are here, it has spring potential energy. It's not the maximum because it's not stretched to the maximum distance. It's got some spring potential energy, and it has some kinetic energy. So both of those together, when you add them up, should equal the maximum spring energy. So that's what we're going to do, and we're going to use conservation of energy again and solve through this. So 5 is the maximum. The spring constant hasn't changed. That's still 40. So 1/2 40. And then the x value is 0.3. And make sure you square that. Okay. And that's equal or plus the kinetic energy. So the kinetic energy is where the velocity is. So I'm just going to solve for kinetic energy first. This value here, when you do 1/2 40 times 0.3, that's 1.8. So it's 5 equals 1.8 plus the kinetic energy. So if you solve for the kinetic energy, 3.2 joules is kinetic. So then you can use your 1/2 mv squared equation. So 3.2, which is the kinetic energy, equals 1/2 the mass, which is 2, and then the velocity squared. So the 1/2 and 2 cancel. You take a square root of 3.2, and you should get v is equal to 1.79 meters per second. Just thinking through this, it makes sense that it is less than the answer before, because this is when all the potential was changed to all kinetic. This is somewhere in between. I don't know if it's positive or negative because I'm not sure exactly which way it was moving. It depends on what time in the cycle, if it's going to the right and slowing down, or if it's going to the left and speeding up. But we know it's not 0, where the velocity would be 0 at the extreme, and it's not 2.23. So it's got to be between those two, and our answer came out to be 1.79, which is fine. All right, you would do basically the same thing for E here. We would just switch out. Instead of having 0.3, you'd put 0.4. At 0.4, it's closer to the extreme position, so I would imagine it slows down as we get to that point, and it does. It's actually 1.34 for that. So I did this already, but if you wanted to try it on your own, you could do the same kind of work. This number here is going to change from 0.3 to 0.4. This number is going to get bigger, and then you can solve for the velocity the same way we did before. For accelerations, you're going to have to use the net force is equal to ma, and the only force acting on this that is causing it to accelerate, if we did a free body diagram, is the restoring force. So Fr is what we're trying to figure out. So this says at the equilibrium position. Equilibrium position is x equal to 0, and then the restoring force equation again is negative kx. So if x equals 0, if that term goes to 0, the whole thing goes to 0. So the acceleration at the equilibrium position is 0. We've already talked about that, so that's not too groundbreaking, but hopefully that makes sense. Same idea here, but now we're looking at 0.5 or negative 0.5 for those positions. So again, we're going to use the restoring force is basically the net force, and we can set that equal to ma. So it's going to be, we'll just do it as positive. So 40 times the maximum position is 0.5 equals the mass, which is 2, times a, which is what we're looking for. So if I divide both sides by 2, it'd be 40 divided by 2 is 20 times another half is going to be 10. So the acceleration here, depending on which position it's at, if it's at positive 0.5, it'd be a negative 10 meters per second squared. If it was at the negative 0.5, it'd be a positive 10 meters per second squared. And that makes sense because the restoring force, the acceleration is always opposite to the direct, or the restoring force and the acceleration always agree in terms of their direction. Again, similar kind of work here. You're just going to change in 0.3 for 0.5. If you did that, you should get, let me see, we're on letter H here. So you should get positive or negative. This one is, since it's a positive 0.3, it'd be a negative point, or it'd be a negative 6 meters per second squared. So you could do that too. So you can see that the acceleration is not constant. It's a varied acceleration. So you can't do the typical kinematic stuff that we have done in the past to try to solve these problems. The net force at the equilibrium position, that's still 0 because you're not stretched or compressed. We talked about that already. The net force at 0.25, you do 40 times 0.25 to get the force. So 40 times 0.25 is just 10 newtons. It would be a negative 10 because it's a negative kx. So that's fine for that. That was J. And then K, it says the position of oscillator when the kinetic energy equals the potential energy. So if they're equal, they're both 5 is the total energy, and if you split that in half, it'd be 2.5. So we want to find the position, so that's going to be based on potential energy because that has x in it. So the US is equal to 1/2 kx squared. And again, like I said, we're the US plus the K should equal 5. And they're both half, right? So if you split 5 in half, it's 2.5, 2.5. So we're going to 2.5 here, 1/2 of 40, and then x squared. So you divide through by 20 on both sides to get rid of the coefficient. And then you got to take a square root. This position, most people think it's halfway. It is not halfway. It is actually 0.35 meters. So at 0.35 meters, that is where half of the energy in this oscillation is kinetic and half is potential due to spring. Okay, so the last thing we're going to talk about here is the concept of how we represent simple harmonic motion using a kind of circular type motion and the reference circle. So this visual is just demonstrated here on this this situation. So we have our oscillation of this mass on a spring oscillating back and forth and back and forth. So this would be like our equilibrium position here. So it's oscillating between the maximum compression and maximum stretch. And the circle is going around. So this green dot is represented by this green dot here. It's the same idea. So like it's over at the maximum, it's at the equilibrium position here, and then it's at the minimum or the maximum compression, and then it goes through. So you can hopefully kind of mirror that out. This motion we can use, since it's a circle, we're basically looking for the x position. So if we put this in a triangle, x would equal, a is the amplitude, that would be like the maximum distance, a, and it'd be a cosine of theta. So theta is the place in the angular displacement that it is. And theta, we can use some different ideas to represent that. So that's what we're going to do. So A equals cosine theta. If we did angular speed, theta was equal to the average speed, omega, times t. So like we know the angular frequency times the time. And then angular frequency is 2 pi f, or 2 pi divided by t. So this is the equation that we're going to use. So you don't have to worry about deriving this really, but this is an equation that we use to represent and be able to find the location of an object in simple harmonic motion at any time. So if we know the time and we know the frequency or the frequency of oscillation, we can figure out, and we know the amplitude, we can figure out exactly where it's located. This is based on cosine. So coming back to this, cosine means at time equal to 0, it's over here at a positive value. And that's what we graphed out. So like when we had x, if you look at the x graph, we go back here, it went like this, came back, and that's not exactly perfect in terms of the heights and everything. But at the time equal to 0, the amplitude was at a maximum, and then it comes back after one complete cycle and it's back to the maximum amplitude. So so that's okay. The one kind of thing you have to be careful with is you have to use radian modes for this equation. This is the only equation in the whole course where you have to use radians in your calculator, but make sure you do that, okay? So let's go ahead and get into the last example, and this is the last one for the video. It says starting at time equal to 0, a spring block oscillator takes 1 minute to make 30 complete oscillations. Its maximum displacement is 0.4. Assume the position is at positive 4 meters at time equal to 0. So if we stretch this out, if this is the equilibrium position again, we're starting at this point where it's at its maximum amplitude. And then it's going to oscillate through kind of these positions. It's moving to the left. It's going to keep moving to the left through that point, and then it's going to be compressed, the maximum compression. And then it's going to start moving back. So I like drawing this out because I think it visualizes what's happening, and it keeps moving that way. And eventually that's going to be one complete cycle. So this is going to be the period of oscillation. So this is where the time is equal to one complete cycle. This is where time is equal to 0. This would be time equal to half a period because it's halfway through. So it would be the period divided by 2. This would be half of that, so that would be a period over 4. Excuse me. And this would be 3/4 of a period. at this one, time equal to 3/4 of the period. So that's the different time values that when it reaches different positions. Okay, so so what we're going to do is we need to use this time and this oscillations to figure out either the frequency or the period. So period is just the time for one cycle. So if it takes 1 minute, which is 60 seconds, to complete 30 cycles, the period of oscillation would be 2 seconds. So like every 2 seconds, it would go through one of these motions and it would start over. So it would just keep doing that. So the period is 2 seconds. If I wanted to calculate the frequency, it'd be 1 over the period. So that would be 1 over 2 or 0.5 seconds. Okay, so we've calculated those, and that's important because we're going to use this x as a function of time equation. So x as a function of time is equal to a cosine 2 pi f times t. And this t is the time that you're at. That's where you're trying to measure it at. 2 pi and f are all constants, so that's fine. A is a constant. So a is the maximum displacement, so that's 0.4. So it's starting at positive 0.4. And we're going to do cosine of 2 pi f. F is 0.5. So that's 0.5. And then that number times t. 2 times 0.5 is just 1. So I could simplify this as 0.4 cosine of pi times t. So this is the part that you put in your calculator here. And we're going to figure out whatever position it is whenever that time varies. So the time that you're going to use in part A is 15. So we're going to put in 15 here. And when you put that in your calculator, you get a negative 0.4. So what does that mean if it's negative 0.4? It means it's over here at this position. It's at the negative amplitude. So this is like a negative 0.4 when it's compressed the maximum distance. It was a positive 0.4 when it was stretched to the maximum distance. So if you think about it, 15 seconds, it's 2 seconds for each one. So that would be 2 seconds to get me here, 4 seconds, 6 seconds, 8 seconds, 10 seconds, 12 seconds, 14 seconds, and then I have another second to go. So if my period is 2 seconds, then half a period would be 1 second. So it's going to get to that point, and that's where we're going to be measuring it at 15. So this equation made sense and works. We could also use the kind of logic that I just displayed there, but that's fine. For part B, it says determine at least 2 times when it's at a position of negative 0.1 meters. So this is where you actually know x already, and you're going to solve for t. So we're looking for the time. That's what we're looking for here. So it's the same equation, except instead of plugging in for t, we're going to plug in for x. So we have negative 0.1 as our position, or x value, equals the amplitude times the cosine, and our other part didn't change, it's still pi t. And we're going to solve for t. So we did this early in the semester when we were solving for an angle. This is basically just the angle. So we're going to divide through by 0.4 on both sides. We get negative 0.25 equals cosine of pi t. You might not have solved something like this before, so that's why I'm kind of going through it. You're going to do the inverse cosine, or the arc sine, or arc cosine. That's really the correct technical term. Again, you got to make sure you're in radian mode. If you're not in radian mode, neither of these answers will work out correctly. So make sure you're in radians for this and for this. So we're going to do that, and that's equal to pi t. And we just want t, so we're going to divide through by pi. So when we divide through by pi, you get t is equal to, the value is, where is it? 0.58. That's the answer it gives you out of your calculator. So 0.58 seconds is where it's at 0.1 negative. And that makes sense, right? Because halfway through, this would be, if we did here, this is negative 0.4, this is at 0. So negative 0.1 is like over here sometime. So again, this is 1 second, half a second would be here. So it's a little past half a second, which makes sense. And what you need to do is you just have to kind of find another time. You can always just repeat it by adding a period to it. So if I add 2 seconds to it, which is the easiest thing to do. So if I add 2 seconds, that's one whole period. That's going to go start. It's going to be here, at this negative 0.1, it's going to oscillate all the way through and come back in 2 seconds. So 2.58 seconds would be another time. 4.58 seconds would be another one. You could keep adding 2 seconds indefinitely. It would just keep repeating like it did in this picture. Like it would just keep repeating and repeating and repeating. So eventually it would continue to get to that position, and you would just measure the time to do that. So anyway, I'm going to stop there. This video is really long. I apologize for that, but I had a lot of information. The next one will be shorter. All right. Talk to you guys later.